In this video, we're going to talk about order 2 tensors. These are tensors that will eventually be representable. Tensors representable by matrices, as we will see in a bit. Specifically in our context, 3 by 3 matrices in 3D. Okay, so recall, order 2 tensors are linear functions that take in as input some vector v. Input is a vector. This is the order 2 tensor, which is a linear transformation, and the output is another vector in 3D for our purposes. Now, before we sort of discuss how these tensors are represented and so on, I guess even before we talk about things in detail, you can sort of see how these would correspond to being represented by 3 by 3 matrices, because what can you do with a 3 by 3 matrix? You can multiply it with a 3 by 1 matrix, which is a representation of a vector, and you get a 3 by 1 matrix. That's a representation of a vector, right? So maybe I'll write that down first, just so that really practically that's the way in which we're going to use tensors as essentially 3 by 3 matrices. But it's good to understand this sort of more abstract theory. So if you had so this thing, which is, let's say, the vector w in some, let's say, coordinate frame 0, you can imagine getting that matrix, 3 by 1 matrix, by operating some 3 by 3 matrix. So this is a 3 by 3 matrix. And Vx, Vy, Vz, where this quantity is the representation, let's say, of W in some coordinate frame. This quantity is the representation of L in that frame, and this quantity is I'm going to put L with a couple of dashes below it to represent the fact that it's a tensor. And the third quantity is a representation of V in the frame 0. Okay. Okay, so that's how tensors will work once you have fixed coordinate frames. But tensors have an existence outside of coordinate frames in some sense, just like vectors have an existence outside of having to be represented by coordinate frames. So let's sort of develop that a little bit. Before we develop the idea of tensors sort of in an abstract context, let's talk about a very special kind of a tensor called a dyad. Okay, dyad. Sometimes also called a dyadic product. Or a tensor product. Or an outer product. Okay. So what is a dyad or a tensor product or an outer product? Denoted, so imagine you have two vectors. Given two vectors, A and B, a dyad formed by the dyadic product of A and B is notated by is denoted by this quantity, sometimes also denoted by the vectors A and B written right next to each other. Okay, so this is notation. Two different notations. Both are acceptable. I kind of prefer this, even though it's a bit more, a bit less concise. It makes it clear that this is not a dot product or a cross product, but it's a different kind of a product called a dyadic product. But this sometimes is convenient to write, I suppose. I don't mind using either notation. Anyway, so what is this new object called a dyad? It's actually a 2 tensor or order 2 tensor, and has the following property. And with the property so what do we mean by an order 2 tensor? We mean it's a linear transformation so of vectors to give vectors. So what is that linear transformation? So if we have a dyadic product between A and B, right? So let's say this is our L. Our L operated on some V is basically your dyadic product operated on V, and it's defined. This is the definition. It's defined to be equal to the vector A times a scalar, and the scalar is B dotted with V, where this is a dot product. Okay. Okay. So vector A times, by which we mean scalar multiplication by the scalar, which is obtained by taking the dot product of B and V. Okay. So that's the definition of this dyad. So we've defined this quantity or this object, and this is how the object behaves. It's a linear transformation because, well, it consists of essentially a dot product and scalar multiplication. Right. So and it's clearly linear in V. Okay. So anyway, so that's called a dyad, and we will see that general order 2 tensors can be represented in terms of dyads. Okay. Anyway, so let's get back to the idea of developing order 2 tensors. Like we discussed, order 2 tensors are linear functions that take us from vectors to vectors. All right, so examples, of course, any linear function that takes vectors to vectors is worthwhile, but in our context in mechanics, the following things sort of come up naturally: rotation tensors, by which we mean rotation operations. Basically, we mean rotations of tensors. because it's a linear transformation, and it takes one vector and gives you another vector. What else? It turns out moment of inertia is a tensor. As we will see, it's going to operate on angular velocity and give you angular momentum, for instance. So we'll talk about that. In sort of mechanics that involves deformations, we can have, for instance, the strain tensor, the stress tensor, and so on. Okay, so these are all all of these can be eventually represented by 3x3 matrices, but like we said, just like vectors, it's good to sort of have this abstract understanding of them as linear transformations. Okay, so that's an aside. Now, let's say we have some linear transformation like so of some vector v. Like we said, this is a vector, this is the linear transformation, the tensor, and this is the vector. And we can expand this out. So let's say this is equal to Vx Ex plus Vy Ey plus Vz Ez. And just like we did for order 1 tensors, we can expand this out by using linearity, the properties of linearity. So essentially you will get, well, let's do this. You can do this step by step if you want. Okay, and that's going to be equal to Vx operated on this guy plus Vy operated on Vz operated on Ez. Okay. Okay, so now that we have this expression, we can introduce some new notation. Essentially introduce notation that says L1, this is some vector, L of Ex. Because L is an order 2 tensor, it's operating on a vector, it will give you another vector. So let's call that vector L1. Say vector L1 equals this linear transformation operating on Ex. Vector L2 is the linear transformation operating on Ey. Vector L3 is the linear transformation operating on Ez. So we can write W equals, well, let's just use this notation in this. We get Vx, well, actually maybe again I should have used Lx, Ly, Lz instead of L1, L2, L3. Let's get back to this. So we have Lx, it's a vector, it's not a component, it's a vector, and then Vy, Ly plus Vz, Lz, something like this. Okay. Each of these quantities is of the form a vector times a scalar. Okay, this is a vector, this is a scalar. So let's write that in that form. So this is Lx times a scalar, which is V dotted with, instead of Vx, I'm going to replace that with E dot V. And then for this thing, it's this vector times the scalar. Actually, instead of writing the scalar in this manner, I'm going to write it as v dotted with ex, and this is v dotted with ey plus lz. Vz, I'm going to write it as v dotted with ez. Okay, that's still the vector w. And now we can notice that each of these terms is exactly in the form a times the scalar, which is b dot v, which we can replace with this dyadic form. Instead of a times the scalar b dot v, we can write it as this dyadic form a outer product b, tensor product b, operating on v. Okay, so that's what we shall do here. Well, I suppose I really wanted to write it in this manner, ex dot v, because dot products are commutative. It doesn't matter which way you write it, which order you write it. The order doesn't matter for dot products. They do matter for cross products, as you know, but they also do matter for outer products. Okay, easy dotted with v. Okay, so let's use this quantity, and so say because, so use a equals a times b dot v. Okay, so using that, we have Lx outer product ex v plus Ly outer product ey v plus Lz outer product ez v. Okay, so that's this vector w, or we can write the transformation in this form. It's basically the sum of these three quantities. Okay, so L of v equals okay, so this outer product plus this outer product, and then this outer product. It's not a unit vector. And the whole thing operating on V. Okay. So what is this quantity? Notice that this is a vector, this is a vector, this is a vector, and it's got, each of these has three components. We can write Lx, the vector, as Lxx Ex. That's a scalar. This is now a scalar. Plus Lx or Lyx Ey plus Lzx Ez. Okay. Similarly, Ly is Lxy Ex, Lyyey plus Lzy Ez, and Lz is Lxz Ex plus Lxz, or sorry, Yz EY plus L ZZ EZ. Now, if we introduce this notation, we can sort of go back here and plug in these three vectors in here and see what the resulting vector is. Okay, so the resulting vector W, recall, is Vx Lx plus Vy Ly plus Vz Lz. And we can plug in Vx, this whole thing, in here. We can expand it out if we want. Okay, we can combine the EX terms, EY terms, EZ terms. Right, so there are EX terms here. LYY VY plus LYZ is VZ. Okay, now this should now, so this is basically your W, right? That's basically equal to WXEX plus WYEY plus WZEZ. So what we have is WX, WY, WZ is this matrix LXX, LXY, LXZ, LYX, LYY, LYZ, LZX, LZY, LZZ times Vx, Vy, Vz, where this is the representation of W in some frame, And this thing is the representation of L, the let's say this is a representation of W in the zero frame. This is a representation of L in essentially the zero frame as well. And this is a representation of V in the zero frame. If you want to denote what this L is, this matrix, this 3 by 3 matrix, is a representation of, maybe it's best to say 0, 0. What the two zeros mean is that the input and the output are both represented in frame 0, and L is essentially represented in these two frames. In principle, you can have the input represented in one frame, the output represented in a different frame, and L will then have sort of half and half representations, the input being represented in one frame, the output being represented in the other frame. So this is the sense in which a linear transformation in 3D that takes you a vector from a different vector is as a two tensor. So once you've specified the coordinate frame in which you represent the input and the output, the representation of the order 2 tensor or the tensor is fixed. What we did here in all this is essentially develop a mathematical language that goes beyond just this 3 by 3 tensor. We may not use this all that much, but might be good to sort of have it at the back of your mind that there is this more abstract notation that doesn't necessarily rely on coordinate systems and so on, that sort of speaks a language of general linear transformations. But once you have a particular coordinate frame like ex, y, z, then you can represent the tensor in terms of, one way to think about this matrix or the action of this tensor is, how does the tensor act on the individual coordinate axes, ex, y, z. Those three vectors are in some sense encapsulating the action of the whole tensor, right? And in fact, the columns of those matrix are actually how represent the outputs of the original tensor acting on the individual coordinate axis. In any case, let's stop there. And like I said, mostly we will be using this 3 by 3 matrix representation, but it's useful to understand this broader notation and background, just in case you are reading a book or anything like that that uses this language.